So solving an absolute value inequality with the first method has us split the absolute value into two, right? When the absolute value goes away, we rewrite the same inequality twice, and in one of them, we make the quantity and the absolute value its opposite instead. And then solving each of those inequalities separately gives us these two simplified versions. M is less than 10, M is greater than -6. And then by diagramming those two things out on a number line and looking for their overlaps, choosing and because our original had a less than sign after the absolute value, gives us the overlap, which is our solution, the interval from -6 to 10, which is open on both sides. So open meaning we choose the parentheses for both. So that's the first method of solution. The second method is a little more straightforward in some ways. It's going to take away some of our ability to make wrong choices. And the idea behind the second method is to solve the equality instead of the inequality. Anytime we can replace a greater than or a less than sign with an equal sign, usually a good idea because inequalities are slippery, right? Sometimes they reverse themselves, sometimes we make the wrong choice when it comes to how to combine them together and so forth. So this method begins with us replacing that less than sign with an equal sign instead. And thinking about, first of all, how does that change the game? M minus 2 is not less than, but now I'm going to write equal to 8. The idea is that we can figure out something about where this quantity is less than 8 by first finding out where this quantity is equal to 8. And then afterwards, doing some additional work to figure out how to navigate that difference. So using the same principle of how to split apart an inequality, how would I split apart this equation into two equations that we can then solve? In other words, when its absolute value goes away, what do we get? What gets left behind? So again, we'll just write it twice. M minus 2 equals 8. M minus 2 equals 8. Just write two identical copies of itself. And then in one of those two identical copies, we'll just reverse. We'll replace the left-hand side with its opposite, the quantity which was inside the absolute value. So again, anytime an absolute value goes away, this is what happens, right? It leaves behind both itself and also its alter ego, its opposite. And now we can solve each of these two equations separately. And solving equations is a happy thing, right? There are no inequality symbols to worry about flipping. There's no sort of silliness that happens when solving inequalities. We get this nice equation, m equals 10, and then as you might imagine, distributing the minus, and then subtracting 2, and then dividing by -1, we get, perhaps unsurprisingly here, m equals -6. So this method begins with us just forgetting about the fact that this was an inequality in the first place and just making it an equal sign and solving this as though it were an equal problem. And you'll notice that what it did for us is it turned up two numbers, 10 and -6, which actually were pretty important numbers in our final answer when we solved it the first way. And so it front loads that work of finding those two numbers, and it leaves the work of the inequality business until later. Because what it does, and I'm going to sort of diagram this out on the number line over here, is it identifies for us the turning points. -6 is a turning point for the quantity absolute value of m minus 2. 10 is a turning point for the absolute value of m minus 2. And it kind of shows us that at those two places, -6 and 10, the right symbol that shows how m minus 2 compares to 8, the right symbol is an equal sign. Right? Yeah, that didn't show up very well. Equals. Right? So at those two places, the left-hand side of this equation is exactly equal to the right-hand side of this equation. And, moreover, those are the only two places on the number line where that's true. That must mean, therefore, that everywhere else on the number line, the absolute value of m minus 2 is not equal to 8. From which it follows, by something that mathematicians call the law of trichotomy, it follows that either everywhere else on the number line, this quantity is greater than 8 or less than 8. And the good news is, again because of a calculus property called continuity, that we won't talk about in this course, but a couple semesters hence you'll get a chance to meet it. Because of a property called continuity, the entire chunk of the number line between -6 and 10 will all have the same sign in between these two quantities. It'll either all be less than 8 or it'll all be greater than 8. That's the same story over here for this whole chunk of the number line. Either it'll all be less than 8 or it'll all be greater than 8. Same thing with this last chunk. So what these two solutions to the equality do is that they divide the number line into 3 regions. It's like it just takes a scissors to the number line. And we know that each of the 3 regions that we've divided the number line into, and I'm going to shade them with 3 different colors here. Let's suppose that we'll call this the red one, and then maybe between -6 and 10, we'll call that the yellow one. And then from 10 to positive infinity, maybe we'll make that the blue one. So we have these 3 different regions on the number line, and all we have to do then is figure out for each of those 3 regions, do we get a less than sign or do we get a greater than sign? And that's kind of easy to do because all it requires us to do is to check any of the numbers in those respective segments. In other words, whatever is true at -4 will also be true when m is 2, will also be true when m is 0, or 8, or 7.2, or 4.5, or pi, or the square root of 2, or whatever. Any of the numbers in the yellow region are all going to give us the same answer for whether this quantity is greater than 8 or less than 8. And that's cool, because it means that we get to choose now any number from that yellow segment and plug in that number for m and see whether or not we get this inequality to be satisfied or not. So what's an easy number that I could pick from my yellow segment here that will give me not a lot of work to do? What's that? 2. Let's say we pick m equals 2. Right? That happens to be a friendly number to work with here. So if I pick 2 as my m, then all I need to do is test the inequality. So absolute value of m minus 2 is less than question mark 8. Right? When I plug in a 2 for my m, what happens? What is the absolute value of 2 minus 2? Oh, what is 2 minus 2? And what's the absolute value of 0? It's 0. Is 0 less than 8? Absolutely. So we find out that on this yellow region, the inequality is satisfied. Right? We actually do get less than for this entire yellow segment. And so that means that this yellow segment is actually part of our solution. It's part that we actually want to be a part of our final answer because it meets, everywhere on that segment is going to meet this inequality. Absolute value of m minus 2 is less than 8. So maybe I'll just sort of write in here. We want to include this piece in our final answer. Include the yellow piece. Let's take a moment and test the other 2 pieces. I'll go through this a little more quickly. What's an example of a number in the blue piece that I could choose? I could pick anything. Let me just pick 12, because we can actually kind of see it on this version of the number line. If I pick 12 for my number, now I just again have to check and see whether it's true that the absolute value of m minus 2 is less than 8 or not, when m is replaced by 12. Well, what's 12 minus 2? 10, and what's the absolute value of 10? 10, and is 10 less than 8? It is not. Right? So for this part of the inequality, we don't get a less than sign in the comparison. We get, in fact, a greater than sign. And so that means that on this part of the number line, we don't want to include in our final answer. Don't include. And as you might expect, especially based on already knowing what the final answer is, if we do that same test for any number on the red interval, let's say m equals -8, then we're also going to get a no answer. because for there, the absolute value of m minus 2 being less than 8 would imply the absolute value of negative 8 minus 2 is less than 8. But what's negative 8 minus 2? Negative 10. What's the absolute value of negative 10? And is 10 less than 8? We decided already that it was not. And so because of that reason, we also want to not include this portion of the number line. So sort of the amount of arithmetic that we had to do to employ this method seemed like it was a little bit more, right? Because we had to pick 3 different numbers for m and plug them in and see if they worked and do, churn out the value of absolute value of n minus 2. So the arithmetic bar is set a little bit higher for using this method. But the logical bar is set lower. You have to spend less time thinking about, okay, does this inequality need to flip? Okay, do I want an and or an or? And if, depending on which one I want, how do I actually compound those 2 inequalities together? All of those logical hoops that we had to jump through to use the first method, we didn't have to use for this method. All we had to do was cut up the number line according to where the equation was satisfied, and then test. This is a very common theme, by the way, for something you're going to do quite a bit in calculus when you find yourself in a calculus class a couple semesters from now. This notion of kind of figuring out where the turning points are, right? Here the turning points for my inequality were at negative 6 and at 10. And then separately testing each one of the regions that those turning points divides the number line into for some property. In this case, the property is our inequality satisfied or not on those pieces. And then using that as a method of approach to figuring out how to characterize where a certain inequality is true. So for this one, again, solve the equation. First of all, replace whatever less than or greater than sign you have with an equal sign. Solve the equation. That takes care of the whole worrying about absolute value stuff. And then go directly to your diagram and say, well, the equation holds at these 2 places. Now let me figure out what holds on the other chunks just by testing a single number from each of those chunks and seeing whether I need to include it or whether I want not to include it. And the answer that we got here was the same as the answer that we got using the first method, which is good, because if these 2 methods led to different answers, then one of them has to have been invalid way of reasoning. So yes, once we figured out that we wanted to include this piece between negative 6 and 10, and because we didn't want to include negative 6 and 10 themselves, because our original inequality was strictly less than and not less than or equal to, that means that the answer that we get here is, again, the open interval from negative 6 to 10.